Although you might not think about it, radio waves surround us every day. They are what make cell phones, Wi-Fi, GPS, radio astronomy, and yes, even regular radio possible. However, before we get to how a radio works, we need to understand exactly what radio waves are. The first part of understanding radio comes from its name. Radio waves are waves. Let me explain. Go to a lake and throw in a rock. You should see ripples or waves spread out across the water from where the rock hit the water. What is happening is that, as the rock hits the water, it pushes some water out of its way, forming a hollow. The water which the rock displaces is pushed up, forming a circular wall above the hollow the rock created. This also collapses, forming another hollow, and so on. The end result is that circular waves spread out from where the rock hit the water. Because the water has a resistance to movement, that is, it either prefers to either keep moving or stay still, a property known as inertia, every wave is a little bit smaller than the last one. Interestingly, the wave travels across the lake, not the water. If that sounds confusing, I'll try to explain. The water moves up and down when the wave reaches it, but it does not spread outward with the wave. What is spreading outward is the motion or energy of the wave itself. If it is still confusing, picture a row of dominoes. If you knock one over, it knocks the one next to it over, which knocks the one next to it over, and so on. Each domino travels only a short distance, but the motion goes through the entire row. Both of these examples involve what is called a medium. For example, the water is the medium for the waves on the lake. While the things that make up the medium only move a short distance, the motion or energy which travels through the medium moves and forms the wave. Now let's look at the parts of the wave. As you might have noticed, the waves alternate between walls and hollows. There's a wall, then a hollow, then a wall, and so on. The top of a wall is called a crest, while the bottom of a hollow is called a trough. The distance between a crest and the next crest is the wavelength. In a cycle, is a changes done by the medium in going one wavelength. That is, the cycle is a change from one crest to the trough, and from the trough to another crest. The next two terms are the most technical and important. The number of cycles the wave goes through in a certain time unit is the frequency of the wave. That is, if a wave does 2 cycles every second, it has a frequency of 2 cycles per second. The unit for frequency is the hertz, or Hz, where 1 frequency per second, 1 cycle per second, equals 1 hertz. There's one other interesting fact about the lake and rock example. If you throw the rock into the lake harder, it will produce waves that are taller and deeper than the waves you would create if you just drop it into the water. The height of the crest above the normal water level, where this dotted line represents the normal water level, is the amplitude of the wave. Here I'll abbreviate as AMP. The depth of the trough is also the amplitude. There are many different types of waves, including the waves you see in the ocean, sound, and light, to name a few. Let's focus on light for now. Visible light, the light we can see, is a special kind of wave, an electromagnetic wave. These waves do not need a medium to travel through, and can, in a vacuum, travel at the speed of light, about 186,000 miles per second, or, for those who use the metric system, about 300,000 kilometers per second. The frequency of visible light varies. Red light has a frequency of about 430 trillion hertz, while blue light has a frequency of about 750 trillion hertz. It's about 750 trillion cycles every second. If you take a visible light wave and decrease the frequency, that is, make the cycles longer, you get an infrared wave, another electromagnetic wave. Infrared cannot be seen, but it can be felt as heat. If you make the cycles longer again, eventually you get another type of electromagnetic wave. Again, a type you cannot see. A radio wave. Radio waves have frequencies ranging from less than 1 hertz to over 1 trillion hertz, and can have wavelengths from about 100 kilometers to 0.1 millimeters. What makes them useful for communication is that they can travel quite far, can penetrate non-metallic objects, and like all electromagnetic waves, travel at the speed of light, although they travel slightly slower to Earth's atmosphere due to it not being a vacuum. But how exactly do we communicate using radio waves? To do so, we need to somehow use the radio wave to carry information. That is, we need to take what is called a carrier wave, or radio wave of a certain frequency, and modulate it, or combine it with whatever information we want to send. There are 3 main ways to do this. The first is simply switching the radio wave on and off to convey a signal, often via Morse code. This is known as an interrupted continuous wave, or ICW, where continuous wave refers to how the radio wave is essentially unchanged, aside from how it switches on and off. While this does work, it has the disadvantage of only being able to convey simple signals through Morse code. You cannot transmit speech or music via ICW. The second is by modulating the radio wave so that its amplitude varies with the signal you are sending. This is called amplitude modulation, or AM, and is used by AM radio. The third is by modulating the radio wave so its frequency varies with the signal you are sending. This is called frequency modulation, or FM, and is used by FM radio. FM has the advantage of being much less susceptible to static, but it is more complicated. This series will primarily focus on AM due to its simplicity and it being developed before FM. Thanks for watching. Next time we'll go over the parts of a basic radio and discuss how to build a simple one.